lab for oscillation of a spring in 2 dimensions. Today we're going to introduce the system, then we're going to outline the important physics concepts, construct a computer model to model the observations, and then answer the what does it mean questions. Today's system is a spring attached to a mass weighing 0.402 kilograms. We set the axis origin to the attachment point of the spring, giving us an initial position that is negative in the x and negative in the y directions. The initial velocity is at rest. Mass is released. The spring oscillates, pulling the mass both in the x and the y directions, giving us this geometric pattern that you see on the graph. So, important physics concepts that we need to analyze this motion, we need to first start with the forces acting on the mass. And as I showed you in the previous slide, the net forces acting on the mass include the force of gravity and the force of the spring where it attaches to the mass. Since the position of the mass is constantly changing with respect to where the spring is attached, that makes the quantity S constantly change. So with each iteration, we have to recalculate the position, giving us the length of the spring, and then using that to calculate the force of the spring on the mass. So given our starting position and our initial velocity, we predict future positions using Newton's second law, where the final velocity is the initial velocity plus the total net forces divided by the mass times the delta t. And then we use that to find a new position using the initial position plus the final velocity times the delta t. This is a really important line of code in the computational model. L is the vector position of the mass minus the vector position of the spring. So it shows you the new length L, and since it needs to be a vector, we need L hat as well. And then the S, being the stretch, is the magnitude of the length of the spring minus the resting length of the spring, which was the 0.123 meters. When we run the computational model, this is the graph output. So the upper part of the graph is the change in position in the x direction, and the lower part of the graph is the change in y position. At the beginning of the graph, you'll notice it's fairly similar to the observed data. However, as time advances and you get further in the data, you notice that the yellow begins to drag behind the green, yellow being the observed. In the y-axis, the red observed begins to drag behind the blue model data. That is likely due to transfers of energy from the spring mass system into the surroundings. So things like drag, friction, thermal energy of the spring, thermal energy in the mass, etc. We can also use the computational model to model the changes in kinetic and potential energy as the spring oscillates and moves the mass. These are the lines of code that are used to do that. K representing the kinetic energy, U sub G being the gravitational potential energy, and U sub S being the spring potential energy. And you'll notice that it does oscillate back and forth based on the graph. You'll also notice that as the red one increases, which is one of the potential energies, the spring or the gravitational potential energy, then the green decreases, and that's the other potential energy. So you'll notice there's this relationship. When the spring energy is at its maximum, the gravitational energy is at its minimum. When the gravitational energy is at its maximum, the spring is at potential energy is at its minimum, and that's because the length of the spring is changing. You also notice that the kinetic energy oscillates as well. When we have the maximum potential energy, either being the spring or the gravitational potential energy, you'll notice that the kinetic energy is 0. And then when we also have that oscillation back and forth with that kinetic energy as the different potential energies are oscillating back and forth as well. So what does it mean? Is the energy principle satisfied? Yes, in the model, energy is conserved, the total energy of the system remains constant. However, when you compare the model to the observed motion, we see that there is energy being transferred to the surroundings in the real system. That is the component that we call Q. According to my calculations, the period in the x direction was 1.66 seconds, which would yield, using the period, a K of 5.95 for the stiffness of the spring. The period in the y direction was a little less, 1.54 seconds, yielding a K of 6.43, which was significantly lower than the 6.83 that we were given.